Okay, in this lesson, I'm going to explain pure resistance, pure inductance, and a capacitor in AC circuit. The first one, in pure resistance. In pure resistance, for example, when the resistance is connected with an AC source, as you can see in this figure, in the case when the switch is closed, what will happen? Both the current and the potential difference, okay, passes through, and the current passes through the resistance, and both potential difference and the current increases and decreases together. And the phase difference between, for example, this is the current across the resistance, and this is the potential difference, okay, VR, both potential difference and current are increased or decreased together. It means that there is no leads and no lags between the current and potential difference, okay? So the reading of the ammeter in this case, for example, when we connected an ammeter with the circuit, so you can see that both the voltmeter and the ammeter are increasing or decreasing together. When the potential difference reaches maximum value, the current also reaches maximum value. When the ammeter reads the zero current, the potential difference and the voltmeter also is reading zero voltage. Okay, so we can say that in pure resistance, in what? In pure resistance, are the phase difference between the current and potential difference is zero. Okay, the phase difference is zero, and both voltmeter and the ammeter are increasing or decreasing together. Okay, so the phasor diagram, it should be like that. Look, the red curve is for the current and the blue curve is for the potential difference. As you can see in this figure, when the current is zero, potential difference also zero. Okay, look. When current reaches maximum, the potential difference also reaches maximum. When the current zero, potential difference also zero. What do you mean by that? So what does this figure indicate? This figure, this phasor diagram tells us or indicates that the reading of ammeter and voltmeter are increasing or decreasing together. Okay, there is no lead and lag between the potential difference. Okay, in pure resistance, the resistance has no relation with the frequency. The resistance in this circuit does not depending on the frequency, so you can finding the resistance at each instant. R is equal, according to Ohm's law, is equal to V over I, Vm over Im, or V potential difference across the resistance divided by the current across the resistance. Okay, so in pure resistance, the equation of potential difference and current can be represented like this. This is the equation of potential difference across the resistance, and this is the equation of current across the resistance. For potential difference, VR is equal to Vm sine omega t, IR is equal to Im sine omega t, without leaks and lags between the potential difference and the current. And according, so Ohm's law, in pure resistance, they obey the Ohm's law. You can finding resistance at each instant. Resistance equal to Vm over Im, or VR over IR, or VE over IE. The power is never becomes zero in resistance. Why? Because in the resistance, the electrical current or the electrical energy is converted to what? To the light energy and thermal energy. What does it mean? It means that when the current passes through the resistance, some of the power is dissipated. Okay, some power will be dissipated. So the power dissipation can be calculated by I squared R. Okay, how can you find the power dissipation in the resistance? Power dissipation P loss is equal to what? Is equal to I squared R. And power is equal to IV. This is the power of the circuit. You cannot finding the power dissipation by using this equation. So it is very important for the students to make this important distinction or difference between the power of the circuit or power lost. Power of the circuit is equal to IV, but P lost is equal to I squared R. Okay? So to find the generated heat as energy, okay, the energy lost, the energy converted to heat, you can use this relation because, as you know, E is equal to what? Or power is equal to energy or work per unit time, E over T. E is equal to what? If you rearrange the equation, P times T. So instead of P, you can write V squared over R, or you can write I squared R times delta T. Okay? This is about the pure resistance. The second one is about the pure cell of inductance. In pure cell of inductance, the second one, in pure cell of inductance, when the coil or inductance is connected with an AC source, so the current I and the potential difference across the source, across the circuit, in that case, when the current reaches the coil, all the current is converted to what? To the magnetic field. All electrical current or electrical energy is converted to what? To the magnetic field. As you learned in chapter 5, when the current passes through the solenoid, all the current is converted to what here? The current is converted to the magnetic field. So in that case, it means that when the current reaches maximum value, the reading of potential difference is 0. And when the potential difference reaches maximum value, the current is 0. So that is why in the pure cell of inductance, the potential difference leads the current by phase pi over 2. So in that case, this is current IL, okay, and this is potential difference VL. As you can see in this diagram, in this figure, the phase difference between VL and IL, because they are perpendicular to each other, is equal to what? Pi over 2 or 90 degrees. So it means that the current and the potential difference are out of phase. But in pure resistance, the potential difference are current, they are in phase. There is no phase difference. Phase difference between them 0. But in pure inductance, phase difference is not equal to 0. In pure inductance, phase difference is pi over 2 rad or 90 degree. So in pure inductance, which one leads? Potential difference or current? Potential difference. The potential difference leads what? Leads the current by phase pi over 2. Why? Because when the current passes through the coil, the current is 0 and the reading of potential difference is maximum. Okay? And you can represent the phasor diagram between the potential difference and the current, as you can see in this figure. The blue curve is current across the inductance and the red curve is potential difference across the inductance. At this point, current is ready, the ammeter read is 0. It means that the current is 0. When current is 0, what is the magnitude of potential difference? Maximum value. And when the potential difference becomes 0, current is what? Current has maximum value. Okay? So, and so go on. Okay? It means that in pure inductance in AC circuit, potential difference leads the current by phase pi over 2 or 90 degree. Okay? So which one leads? The potential difference leads the current. Potential difference leads what? Potential difference leads current. Okay? Okay. In pure cell of inductance with AC circuit, the resistance in the coil because there is a resistance of the coil. When the current passes through this circuit, this coil will resist this current. The resist of this current in inductance is called what? Inductive impedance. It's called what? Inductive impedance, XL. What is inductive impedance? Inductive impedance is the ratio of the maximum potential difference to the maximum current across the circuit. So XL can be found by using this equation. XL is equal to what? Is equal to omega L, or XL is equal to omega, as you know, is equal to 2 pi F, is equal to 2 pi F L. It means that inductive impedance depends on what? Frequency and coefficient of cell of inductance in the coil. And it obeys the Ohm's law. You can find the inductive impedance at each instant. Vm over Im, VE effective over I effective, okay, or VL over IL, okay. So this is about the inductive impedance, and no energy dissipated, no power dissipation, no energy loss in the inductive impedance. Why? Because the current does not convert it to the heat for the pure cell of inductance. Be careful, pay attention please. For pure cell of inductance, no power dissipation. There is no power dissipation. Power dissipation is zero. It doesn't obey the Joule's law, okay? Why? Because the electrical energy converted to the magnetic field. The equation of potential difference and the current you can represent, as you can see, because the potential difference leads the current, you can represent the equation of potential difference, Vm sine omega t plus pi over 2. Why this is plus? Because lead. Okay, because potential difference leads what? Leads the current by pi over 2. Okay, and the current is equal to Im sine omega t. When you write the phase difference with the potential difference, you are not required to write the phase difference with the current. Okay, and also you can say potential difference leads current is the same statement with the current lags behind the potential difference, and you can find XL, inductive impedance, at each instant, Vm over Im, Ve over Ie, or VL over IL, and also is equal to omega L and 2 pi FL. The power is zero, does not work, no power dissipation, and the energy is stored in the magnetic field generated by the current. Okay. The last one, in capacitor, AC capacitor connected with the AC source, as you can see in this figure. We have an AC source is connected with capacitor. The capacitor is a device that can be used to store the electrical energy. Okay. In that case, the ammeter is connected series to the circuit and the voltmeter is connected parallel to the circuit. When the current passes through the circuit in the capacitance, the current cannot pass through and continue pass through the circuit. Why? Because of the capacitance. It means that there is a resistance. What is the resistance here? Is capacitance. This resistance of the current capacitance is called capacitive impedance. XC is called what? Capacitive impedance. XC is equal to what? 1 over omega C. And XC is equal to what? 1 over 2 pi FC. It means that capacitive impedance depends on frequency and capacitance. Inversely proportional with frequency and inversely proportional to the capacitance. Okay? What is the relation between the capacitive impedance with frequency? Inversely proportional. With capacitance, also inversely proportional. But in inductance, capacitive inductive impedance, XL directly proportional to the frequency and inductive impedance. So in capacitor circuit, this is IC, the current across the capacitor. Potential difference VC lags behind current. VC is lags behind current, is opposite to the inductive impedance. Why? Because when the current passes through the circuit, the current is the emitter reading 0 and the potential difference maximum. When the potential difference reading becomes maximum, the current has 0 magnitude. Okay? The capacitor impedance depends on frequency of the voltage and capacitor of capacitance. Xc is equal to 1 over omega c or 1 over 2 pi fc. And you can represent the equation of potential difference and current like that. For potential difference, because in capacitor circuit, potential difference lags behind current. That is why the equation becomes like that. Vm sine omega t minus y minus, because potential difference lags behind current. When you are writing the phase difference with the potential difference, you are not required to write the phase difference with the current. Okay? And the power is 0. There is no power dissipation also in the capacitor circuit. And to find the magnitude of the charge, Q is equal to what? Is equal to Vc, or change in potential difference multiplied by the capacitance. Okay? So, finally, we can conclude that the pure resistance and pure self-inductance and pure capacitor, if in pure resistance we have resistance, in pure inductance of the circuit we have inductive impedance XL, depending on the frequency and coefficient of self-inductance. And the last one, in capacitor circuit, we have capacitive impedance. It means that XC. What do you mean by capacitive impedance? XC depends on the frequency and capacitance and inversely proportional to the both of them. In the next lesson, inshallah, we will explain RLC series connection with the AC circuit. Thank you for listening.